Hello, my name is Grace DeBoer, and I'm presenting on Palladium Catalyzed Suzuki-Miyaura synthesis of 2,4-nitrophenylthiophene and 2,4-methylphenylthiophene monomer and dimer. So, one of the biggest challenges in the development of renewable energy is the need for batteries. Most renewable energy sources, such as solar or wind power, only provide energy intermittently. A coal plant could, for example, increase or reduce their output depending upon how much people need in a day, but we don't really have control over how much the sun shines or the wind blows. So this is one of the major advantages fossil fuels have over renewable energy, and it's something we'll need to solve if renewable energy is going to become more common. So one reaction of interest for chemical battery production is the thiophene dimerization reaction. A thiophene is a 5-membered aromatic ring with the sulfur at the peak. This is one of them. And this is an example of a thiophene dimer, two thiophenes connected together with a carbon-carbon bond. And in a thiophene solar battery, this bond will be created when sunlight strikes the thiophene monomers. And then we can store the dimers until we need energy again, perform a reaction, break the bond, release the energy. And we will have leftover monomers, which we can excite with sunlight again and make a rechargeable battery. And thiophenes are ideal for these kind of reactions because they're small. They're small, but they have a lot of energy in them. And they can undergo reversible reactions, so we can have a rechargeable reaction. So to study these kinds of reactions, Carroll students need one thing, lots and lots and lots of thiophenes to test. So my job was to synthesize a whole bunch of thiophenes. So I'm only synthesizing para-substituted thiophene, aryl-thiophenes, where the thiophene is attached to a benzene ring, and then at the opposite end is another compound. And the reason I'm only testing para-substituted thiophenes is for the ease of comparison. Where the bond is on the ring can affect the energy output of, say, the dimerization reaction. And it's just easier to compare apples to apples and oranges to oranges, if that makes sense. I'm also making both monomers and dimers of my thiophene compounds. And the monomers are for use for another student, the student who's working on the electrochemistry for turning these into batteries. And the dimers are to test this student's work. So in the same way, it's hard to grade a test without a key. It's hard to do spectroscopy of a large complex molecule such as this without having an idea of what it looks like. So if the student doing electrochemistry knows what a dimer looks like and how it behaves under like an NMR or a mass spec or a GCMS, they should be able to tell whether or not they've synthesized the dimer. So to make these monomers and dimers, I joined together an aryl boronic acid, one of these, to a bromine substituted thiophene monomer or dimer, using a transition metal catalyst. And researchers at other universities have performed these kind of reactions with very high yields, up to 77% in cases. And I've been following the procedure developed by scientists at the Laboratory of Energy Conversion and Storage Materials at Beijing Normal University. And they used a palladium catalyst to perform Suzuki-Miyaura cross-coupling reactions between thiophenes and aryl compounds. So here's a brief little overview on how Suzuki-Miyaura synthesis works. Brief because this reaction is very complex. It literally won a Nobel Prize. Essentially, the palladium catalyst will act as an intermediate for the formation of a carbon-carbon bond between the thiophene and the benzene. It will be inserted in between them, form a bond between them, so they're both attached to the palladium, and then something cool called reductive elimination will occur. And the palladium will drop out of the bond and leave the benzene and the thiophene attached to each other. And I performed this Suzuki-Miyaura coupling reaction to synthesize the nitro and methyl aryl-thiophene monomers. So I began by synthesizing the 2,4-nitrophenyl thiophene monomer. And due to unrelated technical issues, this is the only NMR spectra I'm able to present. This is a stacked NMR spectra of the aromatic region of the crude results of a reaction that I assume to be 2,4-nitrophenyl thiophene, as well as the starting materials, 2-nitrophenyl boronic acid and 2-bromothiophene. And looking at these spectra right away, you'll notice that the only peak that's remained in place is this peak, and that's because it's the solvent peak. It's always going to be the same. And this means that the reaction, whatever reaction has occurred, has gone to completion because these starting materials are all gone in this crude product. And another noticeable thing is that the peaks of this product are very, very complex. They're almost lumpy. And what we think happened there is some kind of unintended polymerization reaction has occurred and has overcomplicated these peaks and created a bunch of byproducts, which will have to be cleaned out of the crude mixture, as they could seriously mess with the results should any student attempt to work with the monomers. So, since the NMR was out of commission, for the rest of the experiment, I used mass spec and gas chromatograph results to test my molecules. And this is a mass spec of the crude product assumed to be 2,4-nitrophenyl thiophene. And mass spectroscopy works by breaking molecules into charged chunks and then measuring the size of each piece. And the most important peak in a mass spec is the parent peak. It's the entire molecule minus an electron. The parent peak of 2,4-nitrophenyl thiophene is at 205. And we can kind of see a little peak, but I'm thinking most of the product actually came off later. We've been having mass spec problems as well as NMR problems, pretty much all semester long. And this is the mass spec of the 2,4-methylphenylthiophene, where the parent peak is at 173, and we can actually see that one. Isn't it tiny and adorable looking? And I'm pretty sure the product was still in the column when this was taken, and I just had to run it for longer. But we're still having mass spec problems. Anyway, after I performed my initial purification and analysis, I left the project to another student after this point. The synthesis of more para-aryl substituted monomers and dimers, as well as the devising of appropriate solvent systems for purification, should be the focus of future experiments. Future studies should also be directed at synthesizing a family of thiophene monomers and dimers to fabricate solar energy storage devices from these molecules. So we can study the redox chemistry of the energy storage and release of these bonds and hopefully develop new renewable energy solutions. Thank you for listening to me.